Now let's continue more on starch. So properties of starch, we know it's insoluble in water and the granules, they swell. And the starch in grain, wheat grain, it can actually absorb 12 to 8% of water, but then based on again the stages of cooking process, we will see some changes in the starch granular structure. I really like this figure showing what happens to starch during cooking process, and then we will have more and more examples in the starch chemistry for mixing and baking process, but this is the summary what happens when you are running an amylograph or during the baking process in the oven. So starch granules at lower temperatures, room temperatures, they will be small in size, and as we increase temperature here, the y-axis is showing the temperature, we see that they get bigger in size, they start to swell, and then we see increase in viscosity. They get very big in size, and then here you see very small black dots. Those are the amylose molecules, they are leaving the granules, and this concept is called amylose leaching. They are leaving the granules, and when we have the maximum size of the granules, we have the highest viscosity. And then this crystalline structure is semi-crystalline at the beginning, but then as we cook and as we progress more into the baking process, we completely lose the crystalline structure. And then they are forming a three-dimensional network of gel systems. As we store the food product, then the starch granules, they start to interact with each other, and this process is called recrystallization process. So we can actually have the crystal formation again, and this is what we experience in the staling process. So starch during processing, and we are going to look at in different stages. So dispersed in water and heated, and starch to water ratio and heating method and the speed is going to be very important. Then enzymes we found in the flour or in the dough system is naturally or artificially added by bakers. For example, some flours are sold as malted flours, or sometimes we add alpha amylase during the baking process. Those will be all very important what happens to starch during processing. And here we are actually going to focus on what is the role of starch in milling process. What do we do to starch during milling process? What happens in the baking? And then little bit touch on the malting and brewing, and then the extrusion. During gelatinization, again, water content of the granules, they increase because granules, they swell and they change shape. And then the granules, they lose their crystalline order, and then the starch, they start to amylose, they started to leave the granules, so this is called amylose leaching. And then the granules, they lose birefringence. This is something I haven't talked about yet, but what that means is because starch has semi-crystalline structure, if we look at them under polarized light, we see a cross, and this cross is called Maltese cross or birefringence. During the cooking process, we also lose that, so it disappears. And then we also have absorption of heat. So this is an example of damaged starch granules, and I have other pictures. So during milling process, we apply force and shear to remove the endosperm from wheat grain, and then we apply shear and force to reduce particle size. Remember, starch granules are, I use the analogy of snowballs. They will be sensitive to shear, applied force, and sometimes they will be ruptured. The part of the granule will be like removed from the granule, and then inside the starch is going to be more exposed to enzymatic attack. So we can have physical damage during the milling process. And sometimes, so we can have physical damage. We can have damage to starch is because of enzymatic changes, enzymatic attack. And we will see those granules in the pre-harvest sprouting. But enzymes, they can also partially hydrolyze the starch granules, and there will be some changes in the granular structure. So starch in bread, starch is the most abundant component of the wheat flour. And then again, traditionally we always put the emphasis on proteins, but then if you look at the starch and how they impact the quality, there are some differences for different varieties, and they will have significant role in the bread quality. Why? Because of setting the crumb, the internal crumb structure, and also staling, how we can increase the shelf life of bread. So there are multiple studies in terms of why wheat starch is unique in terms of baking quality, and how the researchers prove that wheat starch is unique. We can actually take the gluten forming proteins and extract the starch, and if you remove wheat starch and add potato starch, for example, or corn starch, we have shown that actually wheat starch is unique, and it provides unique breadcrumb and bread quality, and that's why it is very critical for optimum baking quality. So certain properties could be described as starch properties, and any starch will do sometimes, but then again, for unique baking applications, wheat starch is very unique. So influence of starch properties on loaf volume, the porosity, and other bread characteristics, there is like relatively less research, and especially compared to role of proteins. But then we know that physicochemical properties, the size of granules, how much A or B granules we have, and then how they are going to behave, how much water they will absorb, they will be all impacted by starch chemistry that is also controlled by the genetics of the wheat varieties. We will talk about different bread baking stages in the later in this course, but mixing is the beginning stages of the bread baking, because we add all the ingredients, and we want to develop gluten, and we want to have homogeneous distribution of all the ingredients. So mixing will result on the dough with target biological properties, and we want to make sure that starch granules are distributed evenly in the dough system. So if we have too short mixing time, we can actually cause some starch aggregation. If we have too much mixing, and then we can actually have some damage to starch granules. So structure is the dough is very complicated than simply gluten with added particles. So starch and protein, they actually have two independent and bicontinuous phase in the dough. They have a unique way of interacting with water. So we have, for the starch in bread during mixing process, we have to consider swelling, water, and absorption. So why? Because as soon as we add water into dough system, all the molecules in the formulation, they will have competition to interact with water, and then there will be also optimum dough consistency development. So factors that influence water absorption: the level of mechanical or enzymatic starch damage, size of granule distribution, and the starch source. So higher the starch damage is higher the water absorption, because damaged starch has higher water absorption. It's because there is more surface on the granules, and then also inside the granules are exposed, and increased water absorption is increasing bread yield. So does that mean that we should have the highest starch damage in the flour and bread formulations? I would say no. So at certain point it's good because it increases the water absorption, but we need intact starch granules for excellent bread quality. So we need to maintain intact starch granules as well. During the fermentation process, the damaged starch is a great source of food for yeast, because yeast is producing some enzymes to convert damaged starch into the glucose. So then yeast is using that as a food source to produce carbon dioxide and ethanol. Then we have the rise in the dough, that's the target, and then we have the fermentation process. So yeast will be first using the damaged starch granules. Again, If we have very high levels of damaged starch, it can cause wet and sticky crumb because we don't have a set internal bread structure. We need intact starch granules to have optimum crumb structure. So this is why the dose of starch enzymes, starch degrading enzymes are extremely important. Alpha amylase, how much we add them, when they are going to be active, they are going to be very important. And the granules are distributed in the gluten network during the fermentation process, and then increasing the temperatures increases the water diffusion, and then it's increasing the leakage of amylose. So the fermentation temperature is going to be very important. And then also the enzymes, since they change the size of the starch molecule, of course they will have impact on the rheology. And if the molecules get smaller, remember they release water. So we can have sticky dough problems if the alpha amylase activity goes out of control. So for the bread in the baking system, we are actually fixing the crumb structure with the gelatinization of starch, and the starch granules in the dough entering in the oven are flattened and folded. And the individual starch granules, we can actually monitor them with the strong and powerful microscopy technologies. So again, there are some studies on replacing wheat starch with other starches, and there was a partial success with tapioca starch, but again, wheat starch is unique. And there are some research that even the surface of the wheat starch is interacting with gluten-forming proteins. Again, the function of starch in the baking is going to be setting the crumb. So, and then also starch in baking, the opening of the crumb cells occurs when there is a sudden increase in the modulus because of starch gelatinization. This is what we have in the baking process. And 3 stages of temperature increase during baking. And then we see changes in the rheology, and then we also see changes in the internal bread. And then we can actually monitor that with the temperature and degree of starch gelatinization. They will be correlated. At the later stages of the baking process, we will know that the starch gelatinization will be completed, and then we will have the set crumb structure. So in the baking process, we have the starch gelatinization, and the crystals are melting, and then depending on the heating conditions, we can have amylose leaching in a less or slower rate. But then the heating influences the degree of gelatinization and the solubilization of amylose. And we can again see what happens to granules are very visible in the dough. But if you look at the bread crumb inside the bread after cooking, we can see that they are not as distinct as they are in the dough formulation. And here the starch is shown with purple, and then the proteins are with green, and then the cooked starch granules are embedded into the gluten network. And this is a nice cartoon again, what happens to starch in the native form, and then also how amylose is interacting with some of the polar lipid compounds. So polar lipid compounds, they penetrate inside the amylose molecules, and as we bake product, the granule structure is distracted. But then when we are aging the bread, we see that there are some interactions of starch molecules with each other. That is why we see a firming of the crumb. But then some of them are partially eliminated and limited because these amylose lipid complexes, they actually prevented those interactions. And now we are going to talk about starch retrogradation and mechanisms of retrogradation of starch. We all know that we have the starch retrogradation because of reassociation of starch molecules with each other. And this is how they come closer to each other and they form crystalline structures, because those interactions are covalent and also hydrogen bonding interactions.